So if you try to map the exact glassed radius of a magical explosion using like a standard linear database, your computer's going to freeze before it even finishes scanning the continent.
Oh yeah, it will literally choke on the math.
Exactly. Welcome to today's Deep Dives, everyone. This is a specialized lo-fi study session, and our mission today is to master the foundational architecture of Geographic Information Systems, or GIS.
So you can map the multiverse.
Right. We aren't just mapping boring old roads and county lines today. We are pulling from a massive stack of sources, research papers on spatial interpolation, texts on TIN data compression, and advanced database indexing guides.
It is a dense stack, but we're going to extract the absolute core insights for you. And, to get us in the right headspace, if you check out the visual backdrop for today's deep dive, we're running this really cool neon vaporwave grid over a fantastical star chart.
It looks amazing, by the way.
Thanks. It's just the perfect aesthetic for visualizing multidimensional spatial data. It's all about these overlapping layers of reality.
Before we actually jump into those layers, though, I have to give a massive shout-out directly to you, Hamid.
Oh, yes, Hamid.
We see you in the comments. And just a huge congratulations for absolutely smashing your SNS exams. We custom-tailored this study session specifically for you.
We really did. And actually, before we get to the math, it is time for the Japanese word of the day. Today's word is geshoku.
Wait, how do you pronounce it again?
Phonetically, it's geshoku.
Geshoku. Okay, I feel like I'm already butchering it.
Oh, same. We humbly apologize for our clunky accents. Please, Japanese listeners in the comments, correct us if we're mangling that.
Yeah, definitely let us know. But what does it actually mean?
It means lunar eclipse, which, perfectly fits that cosmic overlapping vibe we're going for today.
I love that.
Yeah.
Okay, so let's get into the actual architecture. Because before we can map a multiverse, we have to, fundamentally decide how we perceive reality itself.
Right, at least from a data perspective.
Okay, let's unpack this because I'm pushing back on how we normally think of maps. Normally you picture a classic Tolkien-style parchment map.
Yeah, with the little ink drawing.
Exactly. You draw a castle here, a dark forest over there, maybe a river cutting through. They are discrete objects.
Yeah, that's what the sources call the object-based model. Everything has a very hard defined boundary.
But what about things that exist everywhere, like ambient temperature? Or, magical energy, mana density.
You can't just draw a box and declare that the magic strictly exists inside this one square.
Right. It doesn't just stop at a borderline.
Yeah.
So what is the alternative?
So we switched to the field-based model. What's fascinating here is how this completely changes the way you look at your surroundings. You have to stop seeing objects and start seeing, overlapping, continuous layers of energy and data.
Like a glowing blanket over the entire realm.
Exactly. Instead of mapping a specific wizard's tower as a single point, you're mapping the continuous mana density across the whole continent. So it might be super dense at the tower, but it slowly fades out as you move away.
But wait, mathematically, a computer has finite storage. How does it store the concept of everywhere?
Well, it can't, which is why we have to use raster format.
Grid cells, right?
Yeah, exactly. You take your map and lay a massive grid over it, like the pixels on a TV. In GIS, you might use, say, a 20-meter resolution grid, and every single cell holds a specific numeric value for the mana density at that exact spot.
Okay, so we've basically pixelated reality. But what do we do with all those pixels? Because the texts mention 3 specific field operations: local, focal, and zonal.
Right, so a local operation just looks at a single cell in isolation, like what is the total magic in this one exact square meter?
Which is helpful, but it doesn't tell me about the environment around it.
Exactly. So then you use a focal operation. That looks at a specific cell and its immediate neighbors to find a weighted average.
Oh, like checking if you're standing on an isolated spike of energy.
Exactly. If your cell is super high in mana, but the 8 cells around it are dead zones, you've found a spike. And then finally, a zonal operation aggregates data over a much larger predefined area, like calculating the max marginal output of an entire kingdom.
That is a total paradigm shift.
Yeah.
You stop seeing a static drawing, and you just see flows of interacting energy.
It is. But storing a continuous field as a giant grid of pixels causes a massive problem.
Because it takes up an astronomical amount of storage space.
Yes. If you have a high-resolution grid of the entire multiverse, the sheer weight of millions of redundant grid cells for, empty, flat planes, it will literally melt your servers.
Right, so we have to compress it. We need a way to structure this data without flattening the actual shape of the terrain.
And this brings in one of my absolute favorite visual layers, proximal polygons, better known as Voronoi
Oh
diagrams.
man, Voronoi diagrams are so cool.
They are so aesthetic. Picture this in our vaporwave vibe. Imagine scattering neon magical guild halls across a dark map. We define the territory of each guild hall based on actual travel times from the halls, not just random political border.
Isocranes. Those are lines of equal travel time.
Exactly. So the map naturally fractures into these beautiful geometric cellular shapes. Visually, it looks like a stained glass window.
Because every single point inside a specific Voronoi cell is mathematically closer to its central guild hall than any other guild hall.
Right. It defines territories perfectly.
And here's where it gets really interesting, because those polygons hide a math trick, a dual graph.
Oh, yeah, the Delaunay triangulation.
Yes, if you take the center points of those Voronoi polygons, the guild halls, and connect them with straight lines, you create a network of triangles. This is the Triangulated Irregular Network, or a TIN.
And why are triangles the holy grail here?
Because 3 points perfectly define a flat plane. You can't warp a triangle, so instead of a heavy raster grid, the algorithm selectively grabs only the highly significant data points, like the peaks of magical mountains, and connects them into a mesh of non-overlapping triangles.
The sources mention algorithms use a lifting scheme to do this. How does lifting compress data?
It is pure mathematical elegance. Imagine your map point sitting flat on a desk. The algorithm mathematically lifts these points up into 3D space, projecting them onto a paraboid.
Basically the shape of a giant bowl, right?
Exactly. Then it calculates the lower convex hull. Just imagine stretching a tight rubber band underneath all those 3D points.
Oh, wow. Okay, I see it.
The flat faces of that rubber band naturally form perfect Delaunay triangles. You project the shadow of that back down, and boom, you have your highly efficient 3D surface model.
So instead of saving a million pixels for a flat plane, it just draws one massive triangle over it.
Yep. And it only uses dense, tiny triangles where the terrain is actually jagged. The efficiency scales logarithmically, not exponentially.
That is incredible. But that brings up a huge issue with real-world data, or multiverse data.
The blind spots.
Right. Sensors are never perfect. What if we only have data from 5 scattered wizard towers across 1,000 miles? How do we guess the continuous values in the voids between them?
That is the art of spatial interpolation. And Hamid, listen closely, because it is time for the mid-episode quiz.
Let's hear it.
Hamid, if you were mapping the blast radius of a Dragon Sins attack, would you use IDW or Kriging to find the most accurate damage field?
Ooh, good question. Let's break down the answer based on the source texts so Hamid can check his work.
Let's start with IDW, inverse distance weighting.
So IDW is the simpler method. It assumes things closer to the blast are impacted more heavily. It's totally deterministic.
Right, it just looks at distance. If you're close, it hurts a lot. If you're far away, it hurts less.
Exactly. But the multiverse isn't an empty void. What if there's a magical mountain range absorbing the blast? IDW doesn't care. It just draws a gradient circle.
Which brings us to the heavy machinery, Kriging.
Kriging is geostatistical. It actually looks at spatial autocorrelation to build a semi-variogram.
Okay, the terminology there is dense. The sources talk about the sill, the range, and the nugget. How does that model an explosion?
So the semi-variogram graphs out the variance. The nugget represents, like, microscale variation, sensor glitches, basically.
The weird magical shield right near the blast causing an error.
Exactly. Then you have the sill, which is the absolute cutoff where the blast wave fizzles out completely, and the range is the geographical distance it takes to reach that sill.
So Kriging uses all of that to find a least squares fit.
Right. It creates a custom mathematical model that accounts for the actual environment, like shock waves bouncing off a mountain.
So Kriging is the correct answer for Hamid. It creates a way more accurate continuous surface.
Totally. But now that we have these complex interpolated layers and triangulated meshes, how does a database actually store this?
So what does this all mean for the architecture? Because, yeah, a standard hard drive is one-dimensional. It just reads a straight line of data.
Right, but our map is multidimensional space.
It's a nightmare. If you want to find all the taverns near you, a linear database has to scan every single tavern in existence to check their X and Y coordinates.
Which would take forever.
Yeah. So we use space-filling curves, things like the Z-order curve or the Hilbert curve. You draw a continuous zigzagging line that folds back and forth until it completely fills the 2D map.
Oh, so you translate the 2D map onto a single 1D string.
Exactly.
Yeah.
So points that are close on the map are mathematically forced to be close on the hard drive. But even then, you need an index. You need arteries.
Like Russian nesting dolls of data.
Yes. You draw a minimal bounding box around all the taverns in a town, then a bigger box around the kingdom, then a massive box around the continent.
So if I search for a tavern, it just checks the big continent box first. If I'm not in that continent, it completely skips scanning millions of data points inside it.
It's brilliant. But it actually introduces a massive vulnerability if we throw chaos into the mix. I'm officially calling this the Hokage protocol.
Wait, really? Okay, let's hear this.
Imagine we let banned from the anime Seven Deadly Sins into this spatial database.
Oh, no.
He would absolutely love this setup because he wouldn't use a standard SQL delete command, right? He wouldn't properly update the archery bounding boxes.
No, of course not. He has the snatch ability.
Exactly. He would just snatch all the primary keys out of the database for fun
Just rip out the crucial reference pointers.
and leave the entire relational model in an immortal mess. You'd have billions of orphan spatial polygons pointing to ghost data.
The whole system would crash, and he'd just be laughing.
Completely.
Assuming ban hasn't ruined our primary keys, though. If we connect this to the bigger picture, querying this data relies on top-K spatial preference queries.
Right. How do we ask the database for the best options?
It uses score functions. You have a range score, which is a hard boundary, like find me a tavern strictly within a 5-mile radius.
But if a legendary merchant is 5.1 miles away, their score is 0. That's too rigid.
Which is why you use an influence score. It assigns higher weights to features based on proximity. So a top-tier healer next door gives massive points, but that merchant 10 miles down the road still gives partial points. It aggregates the continuous influence of the area.
That's amazing.
But this raises an important question. Everything we've talked about today assumes the map is static.
Right.
But what if the multiverse isn't static? What if the mana fields are shifting and the dragon sins are flying across the map in real time?
Oh, wow. You'd have to add the fourth dimension, time.
Exactly. You move into spatiotemporal databases, moving object databases. You have to constantly recalculate their trajectories and velocity to see where their spatial influence will be in the future.
An infinitely shifting map.
Yeah,
That is a wild concept to leave off on.
it really is. Well, thanks for hanging out in the server room with us. Hit that subscribe button and share the stream. Don't let the sin of pride convince you that you've mastered the layers already. Even the strongest Hokage has to keep studying the scrolls.
Yeah. Exactly. Keep it SSL, subscribe, share, like. Get it. Safety first. CO.